Okay, that's a good one to start with. So let's start with that one. I'm going to go as fast as I can to get you guys through. But much of it, I'm going to pitch 5.3 and get as far into 5 as possible. 5.4 is the last section on the exam next Wednesday, Thursday. All right, so remember what we do on these kind? Yeah, remember the game plan? So this is an exponential equation. And what does that mean, exponential? How do you know when something's exponential? Yeah, not just that it has exponents, but that x has gone into the exponent zone, right? X is in power, right? That's the deal. Yeah, so the steps are: step 1, make the bases the same. And step 2, then you set the powers equal, right? And solve it. All right, so give that a try. Make those bases the same, then set the powers equal, and we do one step. So it's 3 to the x squared minus 45, and make that 9 3 squared to the 2x, right? They good? And then that right side is really 3 to the 4x, huh? Because powers inside multiply powers outside. So now the bases are equal. So you can now, as soon as you make the bases equal, the powers have to be equal, right? Because if 3 to something is equaling 3 to something else, those powers must be the same, or 3 to one of them wouldn't equal 3 to the other. It's got to be the case. They couldn't be different powers, right? Or 3 to one of them wouldn't equal 3 to the other. So the powers have to be equal. So now you got to solve that. Now, are you good on solving x squared with equal? You got to be solid as a rock, really, in this class, especially in calculus. When you see x squared, what's the first thing you do?
Move everything to one side.
Yeah, to get a 0. Exactly. Move everything to one side to get a 0. You just got to know that like a knee-jerk reaction. Somebody wakes you up in the middle of the night. X squared equal sign. Get a 0. You just got to know. Get a 0 right away. That's what you got to do. So get a 0. So now, which side? You can go left side, right side. It's going to be easiest to make the front guy positive. He's already positive on the left, so just jump this over here. So x squared minus 4x minus 45. So get a 0, and then step 2 is factor. How do we factor that thing? Yeah, are you good with the factoring thing? Right, so how you doing on that? So remember the factoring, you're looking for what multiplies to be, right? I write FOIL sometimes, same thing, FOIL, or multiply in the end, add in the middle, same thing, right? What multiplies to be 45? Yeah, 9 times 5. Okay, no signs yet. How do the signs always go? What's the rule? Sign in the middle on the bigger. Always. Sign in the middle on the bigger. Always. Sign in the middle. Who's bigger, 9 or 5? 9. So he takes the sign in the middle. Sign in the middle is always taken by the bigger. Right? Minus 9 plus 5, that's minus 4, huh? And they multiply to be negative 45. And then you know it's just going to be opposite, right? Is that okay that I jump to that? You guys know that, right? So then it's going to be positive 9 and negative 5. There's my 2 answers. Good on that one? Questions? We okay? All right, so 49x times 7x squared is 2401 squared. What do you think? Remember what we got to do. We got x's in the power zone, so we got to make all the bases the same. That's the first thought you should think. I got to make all those bases the same. What do you think is going to be the small base number that we can make the left side and the right side all become? 7, huh? The 49's clear enough. That's 7 squared. Okay. 2401, I'm betting that's 7 to some power, like 5th or something. 4th, is that what it is? So it's 7 to the 4th. Just try that in your calculator. Just take 7 times 7 times 7 times 7 until you get it. Keep track of how many 7s that was. 7 to the 4th, it turns out. So see how I naturally come up with that thought? It's got to be a 7 because there's 7s on the left. All right. So now you remember the exponent rules. Powers inside parentheses multiply powers outside. So that's going to be 7 to the 2x. And 4 times 2 is 8. Right? So remember the rule. Powers outside parentheses multiply powers inside, for instance, right? So 2 times x and 2 times 4, right? On those two, it's good so far. Now, what's the 2x and the x squared going to do? They're going to add. Right? You clear on those 2 different sets of power rules. Right? What do I mean? I mean, yeah, those 2 we're looking at right there. 2 matching bases, the powers add. Versus one, like up here we had 1 base with a power to a power. Those powers multiply. Right? Remember all those little rules? So you can take it from there, right? So power equals the power. So we say, okay, so 2x plus x squared is 8. Let's go over here now, right? Once the bases are the same, you know the powers have to be equal. Jump the 8 over there, reorganize it. X squared plus 2x minus 8 is 0. 2 parentheses. What multiplies to be 8? What times what is 8? 4 and 2. Sign in the middle is plus, goes on the bigger. But then the final answer is opposite, opposite. Minus 4 plus 2. Good? All that straight ahead. Questions on that? Solving those? Good? All right. All right, try that one. I'll finish your look. So basically this is e to the x squared is e to the 9x times e to the minus 20. That's what you want over e to the 20th means. Remember that? See how we're just firming up your algebra rules? That's what pre-calc and calc do. You'll know algebra when you're done with calculus. Because you'll know these rules like the back of your hand. You'll never stumble. But right now you're probably maybe a little shaky. You kind of, I don't remember. Right? That's the purpose. Make sure you get those down. Then these combine, right? Because these just combine when they have the same base. I don't care if the base is e. Doesn't matter. Just same base. Those combine, right? I really added those, but adding a negative 20 is subtract 20, right? All right. Now I can set the powers equal. So x squared is 9x minus 20. And then you know the deal. Jump both these guys to the other side. Get a 0. Minus 9x plus 20 equals 0. Factor. We're looking for what? Multiplies to be 20, adds to be minus 9. What times what is 20?
5 and 4.
Yeah, going to be 5 and 4. They're both going to be negative to make negative 9 in the middle, huh? On that one. It's still true. Sign in the middle is taken by the bigger. It's just also taken by the littler. So it'll always be the case. The sign in the middle goes to the bigger. It sometimes also goes to the smaller one. But it for sure goes to the bigger one. So anyway, opposite, opposite, plus 5, plus 4, we're done. Good? Remember all those rules? All right. Okay, so if 5 to the x is 2, they're asking, what is 5 to the minus 2x equal? So they're telling me what 5 to the x equals. I don't have any idea what x is, but they're saying whatever it is, 5 to the x is 2. Find 5 to the negative 2x. How do I do that? I've got to make this look like that, don't I? It's going to seem different than something you normally do. Everybody seeing the general game plan here. I got to make 5 to the x look like 5 to the minus 2x, because that's what they want me to figure out. How do you do that? Well, if I raise that to the negative 2 power, and whatever you do to one side, you have no choice but to do the same thing to the other. Wouldn't that make the left side become 5 to the minus 2x? So then whatever the right side becomes must be it. Let me say that again. You see what I just did there? I just said, well, they want me to make it look like that, so okay, raise it to the negative 2 power. And these things are equal, they told me. So if they're equal and I treat them the same, they'll be equal afterwards. Right? So whatever 2 to the minus 2 is must be the answer. What is 2 to the minus 2? What is it? 1/4. Good. So everybody know that's 1/4? So again, what did negative powers do? They flip the thing and then it becomes positive. Remember that? Negative powers. So you want to be crystal clear on negative powers. Negative powers, they flip. Or they, I just say it flip is true. more generally said, jump to the other side, then become positive. So negative powers jump to the other side. So if it's on the top, over 1, it jumps to the bottom, then becomes positive 1/4. So 1/4 is the answer. What answer? That's what 5 to the minus 2x must equal. It must be 1/4. So I did that. I just took the original statement they gave me, and I raised both sides to the negative 2 power. Why? Because that made the left side look like what they wanted. And then so I just tracked with what it did on the right side. There's testing your knowledge of powers and negative powers and things. You know the power rules. Because that's where we're at. In exponents, it's all about exponents, power rules. So they're saying, all right, got this. Tell us what 12 to the 2x equals. Let me let you think on that one. The same kind of thing, you got to do something on the left side that will make the left side become 12 to the positive 2x. And then whenever you do left side, do the right side because they're equal. Right? And they'll be equal afterwards. If they were equal before and you treat them the same, they'll be equal afterwards. So what do you got to do to that left side? Well, it's the same thing as last time, huh? I thought it was different, but it's the same. It's just negative 2 again, isn't it? Because negative 2 times negative x will be positive 2x. Yeah, all right, so it's nothing different. So both you've got to do it both sides. So what's 11, right? Because they were equal before. I treat them the same. They'll be equal afterwards. What is 11 to the negative 2? What does the negative power do? It's over 1. It flips it to the bottom. Power becomes positive. 11 times 11, 121. We good? Just like that. So that's something we already did. Let me show you. Okay. Let me give you a second. They want you to determine the exponential function from the graph. Work backwards from graph to exponential function. You did it yesterday. Not a graph, but what? Well, what backwards working? What did we do yesterday where we came up with an exponential equation? It's only been 24 hours. First thing we did yesterday. Remember? Remember the tables? Yeah, remember those XY tables they gave you? Isn't that what graphing dots are? Isn't that an X and a Y? Negative 1.5, 0, 1, 1, 2, 2, 4. Remember we did those yesterday. Remember how? And then we looked at the Y's. We say, what's happening on the Y every time? Remember those? What, is it adding the same number every time? If so, it's linear. Is it multiplying the same number every time? If so, it's exponential. What's doing on the Y's?
It's multiplying.
Multiplying by 2 every time, isn't it? Remember those? So just put your graphs into a table and do exactly what we did yesterday, which you remember perfectly, right? Times 2 times 2 times 2. So then it's y equals c times b to the x. Remember that? And what's the b? It's the 2. It's the number being multiplied every time. And what's the c? It's whatever's next to x is 0. It's the 1. So it's 1 times 2 to the x, or just 2 to the x. Remember, the c is the number across from x equals 0. So you could just say 2 to the x. And 1's really not doing anything. Remember that? That was so. Look back at the notes if you're rusty on that. So these graph ones, just turn them into tables. It's the same question. So, all right. So how about 30? So give me that weird. That looks like the hardest of the batch. So they're first off on part A. They're saying what's h of negative 3? So let's do that. So h of x is 1/3 to the x minus 81. Whoops. And we want to ask, what is h of negative 3? So let me give you a second there. Go ahead and plug negative 3 into that function. Exponential. They're again just having us play around with exponential functions. Give you a second there. So 1/3 to the negative 3. That good so far? I just plugged that, that in there. Now what do negative powers do? Flip it, huh? It doesn't put negative in the front. That's the mistake lots of people make. Negatives in the power zone have nothing to do with negatives in the front. Zero. No relationship. Negatives in the power zone simply flip things. They do not change signs in the front. So you want to be real clear on that. So that negative power just flips it like that. So that's just a 3, really. 3 over 1 is just 3. And so what's that? 27 minus 81, which is 50, 40. What is it? 54? Thank you. Negative. And there we go. That good? That's part A. That's only part A, huh? That good? I'm done. No, I better do more. All right, so that's part A. Maybe I'll go to a new screen for part B. Yeah, I'm going to need to. So, okay, so we good on that? Everybody okay with that? Negative powers flip things and then become positive. So they're just, again, just beating that drum. Are you clear on negative powers? Negative powers flip things and then become positive. All right, so let's do part B here. All right, so part B, h of x is 162. So I take that little, well, let me come up here. Take that little h of x is 1/3 to the x minus 81, and we plug in 162 for h of x. Right? Like that. And then I need to solve that for x. Try that. There again, just testing. How well did you learn power rules coming out of algebra? These were all in algebra, but now they're having to really learn better. Solve that x there. Use your calculator. Start by adding 81 to both sides. So 243. Everybody good to there? Right? Okay, so let me give you some help on how I would think about that. I know that 1/3 can be confusing with a fraction, so I would just think this way at first. I would just say, what if it was just a regular 3? I know it's not, and I'll handle that in a minute, but what if it was just a regular 3, to make the thinking simpler for a second? 3 to what power is 243? Yeah, if you use your calculator, just go 3 times 3 times 3 times 3, and times 3, you'll find that it's 5. 3 to the 5th power, right, just by multiplying on your calculator, is 243. But then, but it's not a 3. It's a 1/3, right? So it's not just a 5 I need there. It's a negative 5, because that'll flip it, make it a 3, and then the 5 power will make it 243. So the answer is negative 5. Does that make sense? Because you need to flip it, make it a regular 3, and then 5 of them makes 243. So negative 5 is the power needed. Good? On that.
What about the second part of the question?
Oh, what is the point on the graph? Yeah, well, that just means xy. Whenever they say point on the graph, it means xy. So what did the x come out to be? Negative 5. What is the y? The y is the function value. Remember? F of x, g of x, h of x, 162. That's what they gave us in the beginning. Yeah, the xy, the point. So the negative 5x going with h of x 162 means the point on a graph. If you were to graph the thing, we're not gonna. You would have the point negative 5, 162. The xy, the x, h of x. Right? All right, and then part C is the same thing. It just says find the 0. What's the 0? What does that mean? So part C, I'm running out of room. So part C. So part C means h of x equals 1/3 to the x minus 81. It means make that 0. It literally means make the function 0. A 0, remember on the graphing calculator we have zeros? It's the y-intercept. It's where the function, the y, is 0. So let's just solve that equation, basically. That makes sense? That's what a 0 is. It's where the function is 0. So how do we solve that equation? Jump the 81 over, like that. take your calculator, go 3 times 3 times 3 times 3, 4 times, but we got to flip it. So what's x? Negative 4. All right. That's it. All right. So, all right, we're getting into logs. Have you done logs before? We will assume you know nothing about logs. It's kind of nice. We'll start from the ground floor. We won't assume anything. We'll just start from the ground floor. So basically, they want me to change the exponential to a log. So change from exponential to log. All right, well, let me just give you the simple, here's the log rule. I call it, when you gain or lose a log, the base stays the base. The other two switch. That's the golden rule for logs. When you gain or lose the log word. So I mean like if you don't have a log and like this one, look at this question they're giving to me. There's no log word there, right? So I'm going to put one on. Why? Because they said change it to a log. So I'm going to gain a log word. I mean, I'm going to put a new log word on that was never there. So if you put a new one in there that wasn't there, or vice versa. If they give you one that starts with the log word and they ask you to take it off, they're going to do that too. It's the same deal. Whether you gain a new one or lose one that's there, gain or lose, what do? The base stays the base, the other two switch. That's always the rule. It's pretty simple, and it's the fundamental rule for logs. So let's rewrite it over here. 625 is 5 to 4. Now, who's the base? Yeah, it's, base just means bottom. Like this is the base of the table, right? It just means bottom. It has something on him, right? So the 5's the base. So when I say I'm gonna put in a brand new log word that wasn't already there, right? Because that's what they're asking me to do. Make it a log. So I'm going to put in a brand. There's no log word there. Boom. I'm putting in a log word. What happens when you gain or lose? The base stays the base. So that 5, which is the base, has to continue being a base, right? Base stays the base. So where's it go? Means it goes low down, right? You know how logs have lower down numbers down by the bottom of the G? That's on purpose, right? That's reminding you that thing's a base. It's the bottom, right? It's the bottom. These are called the what? The base spores, because they're the bottom, right? So the base stays the base, and the other two switch. What do I mean switch? Instead of the 5 having the 4 on it, they'll switch, and the 5 will have the 625 on it, and the 4 will go to the other side. I don't care about left, right. I hope I didn't confuse you with left, right. Don't worry about left, right. Don't think, when you switch it, don't worry about that at all. Just think about the fact about which thing the base has. The 5 had the 4 on it. Now it has the 625 on it. That's what I mean by switch. They switch who goes on whom. And we're done. That's all they want. We just changed to log language. In other words, we just did like one to uno or something. We just changed languages. We're saying the same truth. This is the same truth as this. They're just being said in two different languages. In power language, exponent language, and in log language. Same exact truth said in two different languages. That's all we're doing right now is translating. We're not really solving anything. We're just translating languages. That good? All right, try it. Change to the log language. Currently an exponent language. Change to log language. Gain a log word. It doesn't matter. If you want to put the log on the left side, right side, matters not. Put the log wherever you want. It doesn't matter. But wherever you put it, the base will be down by its G, and the other two will switch, right? Left side, right side doesn't matter at all. I just always put it on the left, but it doesn't matter. So I'm gaining a log word that wasn't already there. When you do, the base stays the base. Who's the base? The 4. So the 4 continues to be low down, right? Continues to be a base. The other two switch. Instead of 4 to the x, they switch and it's 4 to the 5.1 and the x goes over there. Is that good? Or if you wanted, you could write it this way. That's the same thing. Both these are good. Doesn't matter which side you have it on, as long as the log's base is 4 and the 5.1's next to it. 5.1 and the x have switched roles, right? Is that good? On that? All right. All right, so now go the other way. Now you're starting with log, change it to exponent. In other words, get rid of that log. So the first thing they want you, I'll just rewrite the original question here. They want you to cross off that log. Rewrite it down below without any more log work, because we're translating out of the log language. So lose the log. And when you do, the base stays the base, the other two switch. So the 8's the base. We agree? The 8's the lower down. When the base stays the base, the other two switch. So instead of 8 to the 64, it's 8 to the 2. The 64 goes over there. Right? And this is like something we already knew, right? We're like 8 squared is 64. We know that. The log is saying, that's what I was saying all along in my weird language. That's what he was saying. Good? Easy enough? All right, so log base 3 of 1. Now they want me to actually like solve the thing. Get an answer for it. I'm going to show you two ways. I'll show you how to do it by hand and then how to do it by calculator. You can do whichever you want on the test. Notice that it's missing the right side, isn't it? There's always supposed to be 3 parts to any log question. There's supposed to be a base, a plug-in, and an answer. Base, a plug-in, and an answer. So what I do is I just go over here and say X. Joe. Well, I'm just giving it a name. I'm just throwing a name down, saying whatever it equals, call it X, because I need to have those 3 parts, to work with the thing. And so now, solving it by hand, I'll do the by hand way here first. Solving this thing by hand, what are you going to do? Well, you're going to do that rule we've been learning. That's why we practiced it, because now it'll come in handy. Lose that log. So go ahead and do the next step. If you lose that log, go ahead and do what we've learned. And see if you can solve for X.
Oh, so you just put it to exponential and log normally?
Yep. So when you lose the log, what happens? Base stays the base. Who's the base? The 3. The other two switch. Instead of 3 to the 1, it's 3 to the X, and the 1 goes over there. Good so far. I translated out of the log language. Now, can you tell me what X must equal? Yeah, 3 to what power is 1? 0. The answer is 0. By observation, right? Just 0. Now, here by calculator, let me show you how you would do it on your calculator. If you want to do this by calculator, on your calculator you have 2 log buttons. Are you aware of that? You have LOG and you have LN. 2 log buttons. Every logarithm has a base, has a low down number. There's no such thing as a log without a base. They have to. Both those buttons, though, on your calculator, they don't show any base, do they? Or they might. Some calculators they might. Anyway, they both really have a base, but they're not showing their base, at least the way I've written them. So does anybody know what is the base of the normal log? It's 10. And what's the base of the ln? It's E. Yeah. Those are the 2 understood bases. We have actually 2 understood log bases. ln stands for natural log. It says it backwards. Logarithmic natural. A lot of algebra was discovered by French people, Spanish and French do the adjectives after the nouns. The car, blue, the logarithm natural. Anyway, so it's natural log. With the base is E. So it's the one we naturally discovered. Remember, I said E was a number we found in nature, right? Pi and E. Anyway, and this is log base 10. Okay, so what? Well, I'm trying to do log base 3 of 1 on my calculator, right? I don't have a log base 3 button, do I? You've got a log base 10 button, and you get a log base E button. It's called natural log. But you don't have a log base 3 button. How do you do logs of different bases than 10 or E? All you can directly do on your calculator is 10 and E bases. How do you, all the logs that are different bases than 10 or E? Oh yeah, some of the fancier ones on the casting natural display, you can enter whatever base you want, so just go ahead and feel free to do that. But if you don't have a calculator that'll do that, what do? It's you just do the high one high and the low one low, and it all works fine. So the high goes high, right? High. I just low. Anyway, there's no use to write all that. So just basically the one that was higher up The one that you turn it into two logs. The one that's higher up goes high, the one that's lower down goes low. Now, why does that work? Because there's a little proof, and if you want to see it, come up after class. But I'm not going to take up class time. There's a mathematical proof I could show you that it's true. But anyway, it is true, so let's just use it. So basically, if you have a log, these are both, by the way, look at these two logs. They're not showing their base. What are these logs? 10. These are both 10, 10. But anyway, you don't have to write it. Just hit the buttons when you can. Just hit log 1 divided by log 3. The top will be 0, so the whole thing is going to be 0. We already knew the answer was 0. It'll be 0. So that's really important. Does everybody see what I'm doing there? When you have a log that's bases other than 10 or e, you let the high go high and the low go low, and you just do two logs. And it's called the change of base formula. Anyway, that's it. I'm not going to bother you with all the details. It works. Come up after class if you want to see the proof. Okay, so log base half of 128. So you could do it by hand, or probably easier, by calculator. Right? Just let the high go high, the low go low, hit the buttons. You can just make that a half into 0.5. Right? You just say, I'm just going to go log 128 over log 0.5. Isn't it like negative 7? I think you get the answer negative 7. Is that right?
Are we just going to use our calculators for this one?
Yeah. So as long as you have it on your scientific, because I don't even remember, but this might be on the part that is. Yeah, I think there might be one. I can't remember exactly, but it could be on the first part where you don't have your graph. So make sure you can do this, on your scientific calculator. I'll do it by hand just for fun. If you want to see it, just put an X over there. Lose the log. Base stays the base. The other two switch. Half to what power is 128? I just think, well, 2 to what power? 2, 7 of them. And so you need negative 7. Because you got to flip it to make it a 2, and then 7 does it. Negative 7. So either way, by calculator or by hand. Is that good on that? All right, so y equals, or f equals, whatever, log base 4 of x. They're saying, what's the domain? I'll just call it f, whatever. What's the domain of that function? All right, we haven't talked about domain of a log. Does anybody know from your algebra days? Not one of the most thrilling parts of algebra is the domain of logarithms, is it? So, all right, so the inside of a log, right, like right there, right? The toaster, like plugging what you plug in, right? That's what domain is, right? What can you put into this thing, right? You can't put knives in the toaster. You can't put tin foil in the microwave, right? So we're talking about what you're allowed to plug in. The domain of the toaster, the inside of the log, must be greater than 0, not equal to 0, not negative. In other words, it must be. You cannot put. Try it out. You guys can take the log of negative 3 or something. Do some negative number. It'll go air. You'll just get an air right away. Or even log of 0. It'll be air. You can't put 0. You can't put negatives into logs, right? And like I said, you don't even have to write it down your 3x5 card. Just test it on your calculator during the test. So the inside of all logs must be greater than or equal to 0. So we have 3 domain issues now. You tracking with me? Do you see the 3 domain issues we have? Right? We have denominators cannot be 0. We have inside of a square root. Yeah, let me write it down rather than just say them out loud. So we have. So let's just call. We have three cases. Number 1, denominators. If you ever have a denominator, cannot be 0. Case 2, the inside. If you have a root, the inside has to be what? Or equal to 0. It can be 0, right? It's a little different. And step 3, the inside, if you have a log, the inside of the log has to be greater. Can't be equal to 0. It's almost like the root, but it can't be equal to 0. Those are the 3. So we're adding to our domain situations. We have a third one now. This will be the last one. There's no more for the whole course. Right? So denominators can't be 0. Inside of a root must be greater than or equal to 0. inside of the log must be strictly greater than 0. So, okay. So they want me to take the inside right there, x squared, and they want me to say x squared, you must be greater than 0. So what's that mean? Isn't x squared always greater than 0? Almost.
Except for 0.
Except for 0. It can't be 0 itself. Right? Any other number, positive or negative, squared will be greater than 0. But it can't be 0 itself. It has to be equal to 0, not greater. So that's effectively saying x cannot equal 0. Right? We good? We happy about that? That makes sense? That's the answer to the question. All right. So number 9, natural log 1 over x minus 4. All right, give it a go. Find the domain. On that one. All right, what do we do? Now we grab the inside and say, hey, inside you must be greater than 0, right? Good so far? For log? Okay. Now how do we solve that? Do we do the denominator? Do we just grab the denominator?
You said it equal to 0.
Set equal to 0? Why is that?
Because it can't be 0.
Can't be 0.
Like the bottom.
The bottom can't be 0. Yeah, that's true, huh? Yeah, x cannot be 4, because that would make a denominator 0. Good point. Yeah, we certainly need to restrict that. X can't be 4. But what about the greater than 0 thing? What do we do to solve that part? How quickly we forget. Remember about last week? We did the greater than, less than. We did the whole section. I did it for like a day and a half. It's funny how you learn something like right when you're doing. This is why you need to, for tests, like next week's test, you need to go over those practice exams. You need to look back over them. Because like when you're doing the homework, like right then, like if I'm giving you this question, you know, this at 1 over x plus 4 greater than 0 back in, I forget which section it was, like 3 sections ago. When they were all greater than, less than questions. Remember we had the 2 types? We had the fraction one and the other. The number line. Do the whole number line thing, remember? It's one of those. When you were in that rhythm, you just done 12 of them in a row. You would have just whipped this out without even batting an eye. But all of a sudden, it's 3 days later, and there's logs, and you're like, this is totally different. No, it's the same thing. But see, that's learning something deeper when you know it out of context. That's what tests different than homework, right? That's why you need to do more than homework. You do homework and then review for a test, because you got to learn things out of context. Like if somebody just throws it at you all of a sudden, oh yeah, fractions greater than or less than. Remember what we do? We set the numerator equal to 0. We set the denominator equal to 0. Then we go to the number line and we test the bounds, pass through. That whole thing. Remember that whole thing? Kind of coming back now? So the numerator equal to 0, no, that can't happen. He doesn't even have an x up there. He's just 1. Denominator, yeah, that can happen. X minus 4 is 0, so that means x is 4. That means go to the number line. What does that mean is at 4 then? Vertical asymptote, right? Remember those? And we just say one side it's going to be positive, the other side negative, or both positive, both negative, I don't know. We test. Remember all this is coming back? You test a point, like you go over to 5, and you say, hey, at 5, is the thing going to be positive or negative? Back here at 3, is it going to be positive or negative? You find where the graph is above and where the graph is below, because we want to keep the places where it's greater than 0, above. All right, so plug in 5. What is it? 1 over 5 minus 4, which is positive. Plug in 3. It's 1 over 3 minus 4, so it's negative. So it's like up on this side. It's like down on this side. So where's my answer? I want where it's greater than 0. I want this section, don't I? From 4 to infinity. This is a parenthesis because we cannot equal 4. Remember all that? See the difference between knowing it out of context and just doing it in the homework? Right? That's the trick. That's the question they gave me when I interviewed. I mean, not that exact question. It was some kind of a domain of a log. You know, when you interview for a job, this was 10 years ago, but for a math job, they give, you know, they usually throw one question at you. It was just funny. I still remember it. But, you know, you do all the standard, you know, what's your philosophy of teaching and blah, 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 blah. But then there's always one, like, just out of the blue, they throw a math question at you just to see if you can solve it off the top of your head, which is always a lot of pressure, especially because these junior college jobs are I have a very nice job for which I'm very thankful. I mean, honestly, I make a good income and I can do it in 30 hours a week and it's fun. I like teaching math. Anyway, a lot of people like these jobs and a lot of people apply. So basically, you mess up the math question, it's over. I mean, there's a bunch of people with master's degrees all in there interviewing. You know, 50 people apply, 10 interview. You know, anyway, so I remember they gave me the math question. It was a domain of a logarithm. I remember going, ooh, yeah, I think I know that. You know, so I was doing it on the board. I did all this stuff and laid it all out. But you just always wonder. I mean, we all make mistakes, right? I'm just thinking the whole time. That's right. I'm not doing something stupid, right? Didn't drop, you know. So the whole time, I finished it on the board. The 5 professors are sitting there. I finished it on the board, and I'm thinking, I sure hope that's right. And Jin He, you guys know Jin He, the Asian gentleman here. He's a fun guy. I like him. Anyway, he goes. You're not really supposed to say things at the interview. He goes, "Good job," in his Asian accent. I thought, oh, good. I got it right. If the Asian gentleman, he just looked smart. If he says it was right, I got it right. Anyway, funny memory. All right, so we have time for one